Hello and welcome to another video. Today we will be learning about polynomial functions and rate of change. Let's start off by looking at the standard equation for any polynomial that is given to you right here. Uh, if you look at the equation, it does follow some patterns. For example, these are all going to be your coefficients. Then you have your exponents starting with the largest one, and then they decrease by 1. Keep in mind that don't always put them in order like this. They could be moved around, but you can always change them yourself to be in descending order, starting with the largest exponent all the way to the smallest one or 0. Your exponents do have to be positive integers, and then your coefficients have to be real numbers as well. The important thing that we're going to be talking about polynomials first is going to be the leading term, the degree, and the leading coefficient. So the leading term will always come from your term with the largest exponent. The degree will be the actual number of the largest exponent, and then the leading coefficient will be the number in front of the variable with the largest exponent. They're all going to be connected to each other. So in this example, since I said this is the standard equation, they're already in order. So I know that the leading term is going to be a sub n x to the power of n. The degree, again, the largest exponent, which will be n, and then the leading coefficient will be a sub n. Let's look at some examples and find the leading coefficient and the degree. The first thing that I'm going to do is I'm going to circle the leading term for example number 1a, where it says f of x equals 3x to the fourth plus 2x minus 7. So the leading term will be 3x to the fourth because 4 is my largest exponent, which will make 4 my degree, and then 3 will be my leading coefficient. Let's look at b. If we look at b, we notice that some of the terms have been moved around. So I'm going to look at the exponents first. I have 12x to the 1, a negative 7x cubed, and a plus 11. You can always write x to the 0 next to the constant. We don't really see it. If you remember from algebra 1, x to the 0 is equal to 1. It's one of your exponent rules. When I look at the exponents, I have 1, a 3, and a 0. The largest one will be 3, so this will be my leading term. If I want to rewrite my equation in descending order for exponents, I'm going to do negative 7x cubed plus 12x plus 11. So this is my leading term. I can use a leading term to get my degree, which in this case is 3. And then I can get my leading coefficient, which is negative 7. If I look at C, I can do the same thing that I did on B and rewrite it as g of x equals 4x to the 0. Now I'm able to see the only exponent that I have, again, is non-negative, so my degree will be 0, and then my leading coefficient will be 4. Next, we will talk about extrema. You actually talked about extrema back in Algebra 2. You did not call it extrema. You called them maximums and minimum. When you talk about extrema, you're talking about a combination of both. We do have two different types of extrema. We have relative extrema or local extrema. You're going to have a relative extrema or a local extrema when your function either changes from positive rate of change to negative rate of change, also known as increasing to decreasing, or negative rate of change to positive rate of change, or decreasing to increasing. You can literally see the shape here. If you're changing from increasing to decreasing, you will always have a maximum. If you're changing from decreasing to increasing, you will always have a minimum. That's what this is talking about here. And then if you have a restricted domain, the endpoints will also be a relative extrema. Keep that in mind. So these two will happen in the middle of the graph when you see that change, and then the other option could be an endpoint like you see here. You can think about what it means for the word local. like your local library, your local park. To me, I relate that to the area. So when I combine that with relative maximum or relative minimum, it's going to be the highest point around the area. You can see here that they're asking us to identify the local minimums and then the local maximums. So if I look here, I'm going to draw my increasing, decreasing lines first to find the ones in the middle, and then I'll worry about the endpoints if necessary. So the first one, I'm increasing to decreasing right here. So this will be a local maximum. In the next one right here at x equals 0, I'm changing from decreasing to increasing. So this will be a local minimum. And then at 3, I'm going to have a local maximum. Again, I can see the change from increasing to decreasing. And then I need to check the endpoints. This is an endpoint. If I look around the area, this is the lowest point in the area, so that will make it a local minimum. So I'm going to make my list. They want the local minimum, so I have two of them. One at x equals -4, and the other one at x equals 0. I also have two local max. The first one at x equals -2, and the second one at x equals 3. Now let's look at the definition of absolute extrema, also known as global extrema. So this will be the largest y value or the lowest y value in the graph. So if I look at this graph, it's the same graph as before. If I look at the two maximums that are given to me right here, I notice that this one is the highest out of the whole graph. Every single point has a y value lower than this one. Now I have to worry about the y value as well because it's going to be part of my answer. So I'm going to say that the absolute maximum for this graph is going to be y equals 2. So I'm going to say absolute maximum equals 2, and it's going to happen at x equals 3. Keep in mind that every absolute maximum will also be considered a local one. Again, if you look at the area, this will be the highest point in the area. But if I look at the whole graph, it is the highest point in the whole graph. If I look at this one, it's only the highest in the area, not in the whole graph, because this point is higher than this one. Now, looking at the absolute minimum, I notice that I have an arrow going down on the right side. So I actually do not have an absolute minimum because there is a lot of points, an infinite number of points that are lower than both of my minimums. So I'm just going to write NA or not applicable for that answer. You do not have to have an absolute maximum and an absolute minimum. It will depend on the graph. So every time you have an arrow or multiple arrows pointing down, you will not have an absolute minimum, and then the same thing will happen for the maximum. Let's look at another example here. They want you to classify each type of extrema for the function below, or write not applicable when necessary. So first, they want to know if you have a relative minimum, a relative maximum, absolute minimum, or absolute maximum. I'm going to draw my increasing, decreasing lines first. I notice that I change from increasing to decreasing. That means I have one max right here. And then when I classify it, again, it is the highest one in the area, so it's local. But I notice that it's also the highest one, the highest point in the whole graph. So it's also a absolute max, is both. So I'm going to go into my answers and write them down. This is the only extrema that I have because I notice that I never change from decreasing to increasing, so I don't have a minimum. And then I have arrows pointing down on both sides, meaning I will not have an absolute minimum either. So relative minimum, NA, relative maximum, NA. Sorry about that. Relative maximum, I do have one at x equals 1. Uh, Absolute minimum is the one that I don't have. That's what I meant to write. and then I do have an absolute maximum that has a y value of 3, and it happened at x equals 1. Okay, let's look at another example. For example B, I'm going to do the same thing, decreasing, increasing, decreasing. So I know I have 3 extrema, because don't forget about your endpoint. So I'm going to make those red first, and then I'm going to start labeling them. So this will be a maximum, this will be a minimum, and then again, this one around the area is the highest one, so it will be a maximum. Since there's points higher than the one on the left, then I'm going to say that one is a local or relative. I notice I have an arrow pointing down, so that will make this a local as well. And then I look at the one on the far right, or at x equals 3, and I notice that again it's considered a local, but it's also considered an absolute. It's both, or global. So when I look at my relative minimum, I have one at x equals -2. When I look at my relative maximum, I have two, one at -4 and one at x equals 3. I do not have a absolute minimum, so I'm going to write NA on both of these. And then because of the arrow that is pointing down on the right side right here. And then I do have an absolute maximum with a y value of 2 that happened at x equals 3. Okay, one more example. I'm gonna go through this kind of quickly since we should already know how this works. So decreasing, increasing, decreasing, increasing. I have one here, and one here because of the changes. And then I have one more on the far left because it's an endpoint. And then the last one will be here on the far right because it's also an endpoint. So on this one, I have 1, 2, 3, 4. I have 5 different extremas. I am going to label them first and then classify them after that. So decreasing to increasing, so this will be a minimum. Increasing to decreasing, the next one will be a maximum. Decreasing to increasing, minimum. And then for my endpoints, this is the highest point around the area, so it will be a maximum. This will be the highest point around the area, which will also be a maximum. Again, they're all considered relative or local before anything else, so I'm going to do that first. I'm going to put relative, 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 and relative, and then I'm going to look and see if I have an absolute maximum or an absolute minimum. So when I look at the highest point in the whole graph, I notice that this is the point in the whole graph. So that will make this point on the far right my absolute maximum as well. And then I notice that this point right here is the lowest one in the whole graph. So this will be my absolute minimum. So I do have all of them on this example. So they want my relative minimums. I have two of them, one at x equals -3 and one at x equals +3. For my relative maximums, I have 1, 2, 3 of them at x equals -4, x equals 0, and x equals 5. Now looking at my absolute minimum, the lowest point in the whole graph is here, which has a y value of -3, and it happened at x equals -3, this one. And then the last one, the highest point in the whole graph, which is here at with a y value of 4 at x equals 5. Keep in mind you are able to have multiple absolute maximums, but they do have to have the same y value, and both have to be the highest in the whole graph. Same thing with minimum. So if you have something that were to look like that, let's say you extend this over here, this point and this point will both be absolute maximum because they both have the same y value of 4. Here are some fun facts about polynomials. So between two real zeros of a polynomial, there must be at least one local maximum or local minimum. If we look at a graph and I have two real zeros, I know that I have to either cross or touch the x-axis. So I either have to go up and then come back down, or I can do the opposite where I go down and then go back up. So those are going to be your local max or your local min. Polynomials of even degree must have an absolute maximum or an absolute minimum. So even degree polynomials will have both of the arrows pointing the same direction. So if we look at an example like this, like y equals x squared plus 2, I notice that both of my arrows are pointing the same direction, like I said, creating the absolute minimum. If I look at y equals negative x squared, I can see that again, both of my arrows are pointing down. So this will be the highest point, creating an absolute max, and that's going to work all the time. Now let's look at points of inflection. So a point of inflection is going to occur when a change of concavity happens. So you either change it from concave up to concave down or concave down to concave up. At a point of inflection, the rate of change of the function changes from increasing to decreasing or from decreasing to increasing. So again, this is the connection between concavity and the rate of change. Remember, when your rate of change is increasing, you're concave up. When your rate of change is decreasing, you're concave down. So I'm going to color code this very quickly with the concavity so that way we can find the points of inflection very easily. So anything in blue will be concave up, again, happy face shape, or parabola facing up. And then again, I see it here on the right side. And then the red part is going to be the concave down right in the middle. So if I look at that, then this is going to be where it changed, and this is going to be where it changed. So I know I have 2 points of inflection. So example number 3 actually wants them. It wants to know the x values where function g has a point of inflection. So I'm going to say x equals -1 and x equals +1. For part B, they want you to look at the intervals and then determine if the rate of change is increasing or decreasing, and then they want you to explain your answer using features from the graph. So from 3 to 4, I'm going to highlight it here very quickly. From x equals 3 to x equals 4. I'm going to say that my rate of change is increasing because g of x is concave up. Okay, now let's look at the interval -4 to -3, which is going to be right here. Let me use my highlighter, yellow, -4 to -3. And I'm also going to say that the rate of change is increasing because I'm concave up. So it's going to be the same explanation as this one. When I look at -1 to +1, which is going to be right here in the middle, for this one, I'm going to say that my rate of change is decreasing because g of x is concave down. Last one, I'm going to be looking between 1 and 2. So that's going to be this part right here that I highlighted in blue. And again, I can see that I'm concave up, so I'm going to say that the rate of change is increasing because g of x is concave up. So again, same explanation as here, we'll go here. Example number 5 wants you to sketch a polynomial on each of the axes provided with the following properties. You do have a domain from -infinity to +infinity. The first example wants you to draw a function where f of x has 2 points of inflections. meaning it will change concavity twice, so I'm going to make a note of that. It also wants one absolute maximum, and then it cannot have an absolute minimum. So now that I have that information, I can start drawing my graph. So I know I need to start with an arrow pointing down. I'm concave down, so I'm going to switch to concave up, and then I'm going to switch to concave down again. So I can see my two changes in concavity now, because again, this is concave down, then it changes to concave up, and then it changes to concave down again. You can see the changes. I do have an absolute maximum right here, and then I don't have an absolute minimum because of the arrows. So that is one possible sketch for the graph. For B, they want a graph that has one absolute maximum. They want to have two absolute minimums, and then they want to have two different points of inflection. So again, I need to have one point that is the highest in the whole graph. I need to have two other points that are going to be the lowest. Okay, so I'm going to start drawing a few points. This will be my absolute minimum. This will be my absolute maximum. This will be my other absolute minimum, and then I will cross here. So I'm going to go up, come back down, go back up, and then at this point I'm going to change concavity. And that's what my graph should look like. So I do have two different points of inflection. One somewhere here, and then the other one right here. I do have two global minimum, one right here and one right here, and then this is just a local maximum. Thank you for watching this video. Don't forget to like and subscribe to the channel, and thank you for watching. Have a great day.